Hello, everyone. Is this on? Yes. So welcome to the AI4OPT seminar. I know this is a bit unusual of timing, but we were really fortunate to be able to have Professor Patricia Hidalgo Gonzalez visiting. So Patty's in town for another event and was very kind to stop by this morning and give a talk. And so Patty's background, she did her degrees at Berkeley, is now a professor at UCSD, has been there now for 5 years. So yeah, exciting to have her here. And okay.
Thank you. Thank you so much, Dan. Do you hear okay? Okay, perfect. I hope the people on Zoom as well. Okay, all right. Yeah, so thank you so much for hosting me. I've never been to Georgia Tech, so I'm really excited to be here. And with all of you, thank you for coming. I know the summer, different schedule, so I appreciate your time as well. And I look forward to interacting with you a little bit if time allows. All right, so as Dan said, my name is Patricia Hidalgo Gonzalez, and I'm an assistant professor at UC San Diego. So in terms of what inspires the work that we do in my lab, I have to start with climate change and wildfires in California. Unfortunately, we're very aware that climate change has been happening and it has had impacts that are very real to Californians and many other citizens in the world. In terms of the IPCC reports, they have been saying this for several years now, that we need to limit our global warming to 1.5 degrees Celsius. And what that means is that we need to get to zero emissions by 2050. So zero emissions economy-wide. So basically, we also need to be thinking about how the integration of renewable energy can take place. And as we think about this question, it brings different challenges depending on the time frame. So we can be thinking about challenges related to second operation, all the way to decades, years of planning, for instance. So the work in my lab spans a broad set of challenges in this time frame organization of open questions in this space. All right, so this is my lab, the Renewable Energy and Advanced Mathematics Lab. And the mission is that we develop mathematical tools that will help the integration of renewable energy. And what we care the most is that these solutions can be implemented in the current legacy systems that we have with the current operations and constraints that we have. That's something that we really care about. I'm very grateful to the funding institutions that I've had, and I look forward to continue working with them. And in terms of research areas, we have a few. So one that we've done a lot of work in is in long-term planning, so capacity expansion planning, looking at the United States and other regions as well. And also, we've been working on real-time operations of low inertia systems, so systems that have a lot of renewable energy online and how to operate those. And in a similar line, using ML and AI techniques embedded with control theory guarantees to operate these new grids. And last but not least, I've also been working on equitable resiliency. So looking at extreme weather and how can we deploy and leverage DERs so we can maintain power even during outages because of wildfires or any other type of extreme weather events. So looking at what's the value that DERs can bring in that setting to still provide power to the people in the face of extreme events. And in terms of techniques, we draw from optimization techniques, control theory techniques, and machine learning techniques. And today, because of time, I'll be focusing on two different papers, each of them. So one, it's in the long-term planning space, and the other one in the real-time operation of inverters in that case. All right, so this is the outline of the talk. So first, I'll talk about the capacity expansion modeling, looking at the value of long-duration energy storage in a zero-emissions grid. And then in the second portion of the talk, I'll talk about another paper looking at non-cooperative games to control learned inverter dynamics of distributed energy resources. And I'll briefly touch about some of the future research that I have and that I'm thinking about, and some ongoing research as well, to see if we have anything in common that you would be excited to talk about afterwards. All right, so let's dive into the value of long-duration storage in a zero-emissions grid. So for this work, we use a capacity expansion model, which is called the switch-WEC model. We have it on GitHub. You can get your own copy. You can clone it. You can develop it for your own region of interest. It's open source. And it's a capacity expansion, and it can be posed as either a deterministic problem or a stochastic linear program. It can also be integer decisions as well. So it's up to you and the question that you have, how to set up this capacity expansion problem. But for the work that I'll show, it was as an LP. And as the capacity expansion model does, it minimizes the total cost of the power system. So that includes generation and transmission, and that includes investment and operation simultaneously optimized. And geographically, this model covers the Western Interconnect. So basically this orange portion of the map here, North America, so includes parts of Canada. Here's not showing it, but includes parts of Mexico as well. And we divide the Western Interconnect in 50 load areas, meaning that we have 50 regions that have a unique or their own load profiles, like hourly load profiles. So we can characterize more of that geographical distribution of the Western Interconnect. So basically think of it as a network with 50 nodes. And in terms of time, the model is very flexible. So it's up to the researcher how to treat time. So for example, you can have investment periods every decade or every year, or only focus, let's say, on 2050 if you would like to. It's up to you. And similarly with the time resolution, it's up to the modeler and the question that you're looking at. And you can, for instance, sample every 4 hours, or you could take a subset of days to represent the entire year, or a subset of weeks, or you can take every single day of the year and model it hourly to capture every possible hour of that year. So it's up to you again and the research question that you're working with. The model is highly flexible. And something that it's important to notice, depending on the capacity expansion, sometimes they optimize in phases. They decide investments first, and then they decide operational decisions. But this one is different. It optimizes simultaneously investment and operation. And the idea behind is that it gives you the technical best. So if you could truly optimize everything, how well could you do, basically? Which we're not saying it might happen in reality, but what would be the technical best, basically. All right, and now to give a sense on the size of the problem and the type of questions we can answer because of the geographical resolution, let's look at the input data and the outputs. So in terms of inputs, it uses all the existing generators in the WEC, which is roughly a little bit over 3,000 by now. It includes more than 7,000 new potential locations for wind and solar, and you can see them here. So each dot is representing a specific farm that could be built that the model can choose to build. So these are the wind candidates and these are the solar candidates. And basically each of these points, they have associated time series of capacity factors, hourly capacity factors. So then the model can truly look at the chronological relationship between load and supply to make sure that it builds what would be optimal for the grid, being aware of that chronological dependency of resource and load as well. And in terms of transmission lines, because we have these 50 regions representing the WEC, they are aggregated. So we aggregate all existing lines in the WEC in this more reduced 50-node graph that we have. And as I was mentioning, as inputs, we use hourly loads by each of these 50 zones that we model. So it's a higher resolution than by state, so we can capture more granularity. And as I was mentioning earlier, we have these hourly capacity factors for wind and solar power, not only for the existing plants that we have now in the WEC, but also for potential new generators that the optimization may decide to build based on these figures. And as a capacity expansion, it requires to have cost assumptions. So projections for the different technologies, projections for fuel cost, and so forth, which come from NREL ATB, which is the classical source for this type of work. And in terms of outputs, it gives you the optimal investment by generator and by decade, if that's what you were modeling until 2050, for instance, if that was your end investment period. It can give you optimal hourly dispatch for each of the generators if you were modeling hourly as well. And it gives you optimal transmission expansion and operation as well, optimal CO2 emissions, and total cost of investment and operation. All right, so now that I talked about the model, let's talk about the specifics of this paper. Now that we have that clear and we're on the same page. All right, so this work, the first author is Martin Staadecker, one of my students. He graduated and it's off to new adventures. But I wanted to show this work that got recently published in the last year. So here we're looking at the value of long duration storage, and there are several conditions of the grid in a zero emissions future. So the motivation of this work is that the future requirement for the United States of storage and the duration for our growing demand that we expect is still unclear. There are a lot of studies, but we still haven't found a consensus of what's going to be needed in terms of storage. So there are some studies that look at, okay, we can get there with only 100% renewable energy grid without storage. There are other studies that say we definitely need storage. And there are other studies that focus more on the clean firm power, so looking at the role that those type of technologies could have. And some other studies even focus on negative emissions with biomass. So there's a wide range on how to approach this net zero question. And the ones focusing on storage, they have been looking at intraday storage, and in some cases, they have been looking at longer durations and seasonal storage, and what's the value of that type of resource. And in terms of the gap of this work, so some studies, they have been looking at LDES or long duration energy storage, but they haven't come from a perspective of modeling the physical constraints of the power system, and their results don't come from a least cost perspective. And the other piece that's very unique to this work is that past work hasn't been looking at how the conditions of the grid affect the type of storage that we need. It's usually they look at it the other way around. So they look at how the different parameters of your storage affects the deployment of that storage. But here we basically flip the coin and we say, let's understand this as a function of the grid that we have. What is it going to require in terms of duration of storage, operation of storage, and so forth. And to the best of our knowledge, we haven't seen studies that analyze the benefits of having storage energy capacity mandates in the WEC and what would be their impact on electricity pricing. So with that, the contributions is that we quantify these benefits in electricity pricing if we were to have mandates for storage. Similarly, we look at how the deployment of LDES changes as a function of different factors. So we looked at what happens if in your region you have a more solar dominant or wind dominant grid. What happens if you cannot expand any transmission because of political reasons, which is, the case of United States. It's really hard to expand transmission. So we need to understand this in case of the spectrum, what that would mean for storage deployment. Also, we also look at as a sensitivity of the cost assumption. So meaning depending on how R&D evolves, how competitive will long duration storage become as a function of that R&D progress. And last but not least, we also look at how the value of long duration storage changes depending on the hydropower availability that we have. So that's looking more at the weather changing, and if we have less water available, how much more storage we will need because of that flexibility that hydro brings. And if we don't have as much water, it wouldn't be there in our system. Because of time, I'll only be focusing on these three. So looking at the electricity pricing benefits of having mandates for storage, what happens if our grid is more solar dominant or wind dominant, how that affects the deployment of storage, and what happens with R&D, how that's going to affect the optimal deployment of storage. All right. So in terms of the problem formulation of how we're using this capacity expansion model, so we are modeling all 365 days of the year. We're focusing only in 2050, and we are sampling every 4 hours. So basically 6 hours represent 1 day for us. And we are enforcing a zero emissions cap for the WEC. So no CO2 can be emitted in this 2050 future. All right, let's jump into some of the results. So this first set of results that I'll talk about are looking at what if we have a grid that's more wind dominant or more solar dominant, how that affects the deployment of storage. So let's focus only on one panel so I can walk you through this and then we can talk about the findings. So here we're looking at a map of the WEC. And we're looking at outputs from this capacity expansion. We're seeing the installed capacity for each of these 50 regions that we have. And in the colors, we're looking at the different technologies. So for instance, in yellow, it's solar power. We see a lot of solar power in the Southwest getting optimally deployed. And that makes sense because the resource is really good in the Southwest of the Western Interconnect. And in the lines, we have the existing transmission in green, and in red, we have the new transmission that gets built according to this optimization. And the other thing I want you to notice is this dot in the middle of the pie chart that is representing the duration of storage that gets deployed, the optimal duration, meaning the ratio between the energy capacity divided by the power capacity. So for how many hours continuously you could provide power if your storage were to be fully charged, right? So the first, and before that, so here I'm showing results for two different scenarios. So one where we force the optimization to build a solar dominant grid. And then in this other scenario, we force the optimization to build a wind dominant grid. And we did that because we wanted to understand how the deployment of storage would change depending on that supply mix. When we don't force anything and we let the optimization build what it's cost optimal, it still builds a solar dominant grid. It's 80% solar to roughly 20% wind. There are other resources built as well, but that's in an approximation. Okay, now we can look at the results. So in this case, we have this solar dominant grid. We see that in most of the regions that have solar power mostly deployed, this dot, it's light pink, and that's representing 6 to 10 hour duration of storage. So that's what optimally supports these regions when they have a lot of solar power deployed. And then when we look at the wind dominant grid that we forced, now instead this dot, it's like darker pink, and that's representing 10 to 20 hours of storage duration, optimally supporting these regions. So we see that the composition of the technologies definitely affects the type of storage that would optimally support those regions. So that's one of the first findings. Then changing gears a little bit, so looking at how does the deployment of LDES changes as we change the assumption for the energy capacity cost by 2050. So before walking you through the table, the idea is that we're not trying to predict the cost of storage, but we're trying to understand if we can build like a lookup table to tell developers, if you get to this cost target or this more ambitious cost target, what are you going to expect for your penetration to be and for what type of product to build that would make you competitive in a 2050 zero emissions future. So to look at the table, each of the rows is representing a distinct scenario where we were changing the cost assumption for energy capacity for storage. So we go from more conservative all the way to very optimistic. So these ones would be more like hydrogen, if you think about it. This is technology agnostic, but you can think about if things work out with hydrogen, it could be this type of cost target. And then on the different columns, we're looking at different metrics, outputs from the capacity expansion. So the first thing that I would like to draw your attention to, it's how much the total energy storage capacity ranges across this range of cost. So when we have the more conservative estimate, it's 1.5 terawatt hours that gets optimally built by 2050. And when we get much more optimistic, it's all the way to 36 terawatt hours getting built, which is a large range. Similarly, for the largest duration of storage in this cost range, we see it going from 9-hour duration in the most conservative approach, all the way to more than 800 hours of duration. So also very different. So if you were to be someone deploying this technology, like working on R&D in this type of storage technology, this gives you a clear understanding of what duration of your product would be competitive at what price point. So basically, if you want to build a product where the largest duration is 30 hours, for that product to be competitive, you will need to reach at least $10 per kilowatt hour of cost for your energy capacity. So that's how we think about this table. We're not predicting, but more showing what would it take for this type of storage to get deployed. And the other result is that in the most optimistic case, we see that transmission needs to be deployed less than 75% compared to the baseline case. So that's a pretty big finding and very relevant in the United States, where transmission is really hard to deploy. So we could find a way around it with storage, perhaps. All right, and now again, changing gears, now looking at what is the impact if we were to have energy capacity mandates in the Western Interconnect. So what this means is that we did a set of runs. So in the x-axis, we're looking at different runs where we were forcing a certain energy capacity to be built in the WEC by 2050. So we went from forcing nothing, whatever the baseline was building, all the way to forcing 64 terawatts hour being built of energy capacity. And on the y-axis over here, we're looking at the prices of electricity that we get as the rule of the constraint of meeting the load. And we see that the distribution, it's what we're plotting in for each of these scenarios. So basically, if you cut across this direction, you're seeing what happens if we are to force a 20 terawatt hour mandate WEC-wide, what would be the price distribution in that 2050 year, if that makes sense. So far, so good? Okay, perfect. All right. So then in this experiment, what we see is that the variability of the LMPs drastically reduces when you get to that 20 terawatt hour mark, meaning that if you were to have these mandates WEC-wide, going beyond 20 terawatt hours might not do much to reducing that volatility or that distribution of your LMPs. So that's an important target that we identified. Now in this figure, we're still looking at the same on the x-axis, these different mandate scenarios, so different runs from our capacity expansion, y-axis still prices, but now we're aggregating them by region. And what we see from this figure is that we still would expect to see regional differences in terms of pricing in this 2050 future zero emissions. As we see today, we do see regional differences in prices. So that was not surprising, but good to confirm that that would still be the case because we have a network and their transmission constraints. Now, in this other figure, we're still looking at in the x-axis these different storage mandates and then y-axis price, but now we're showing the results by time of the day that we were optimizing for. And what we see over here is that the lowest prices were attained between 8 a.m. and 4 p.m. And that makes sense because that's when we have the highest solar power generation, right? And last on this panel, we're still looking at energy capacity mandates prices, but now we're aggregating by month of the year. And what's notable here is that the highest prices are in December and July. And that makes sense because in the Western Interconnect, that's when we have the highest demand. So it reflects what we would be expecting. And across the board, in all these scenarios, we always see that this 20 terawatt hour mark, it's like a tipping point where if you were to increase your mandate for storage, it wouldn't add much more value because then things behave kind of similar beyond that point. So that's our recommendation. Don't go beyond that 20 terawatt hour of a mandate if it were to be implemented. All right, so to conclude this first part of the talk, we saw that depending on the grid composition, if it was solar dominant or wind dominant, different durations of storage get optimally deployed. For solar, we see 6 to 10 hours, and for wind, 10 to 20 hours. Similarly, R&D can play a key role in the deployment of LDES. For example, if it were to achieve an energy capacity cost of $5 per kilowatt hour, that would enable 28 hours of mean duration for storage and a maximum of 400 hours. And this last result, it's if we have different storage mandates, they can help mitigate the electricity prices volatility and also seasonality in a zero emissions grid. All right, so that was the first part. Now we're changing gears very drastically. Now we'll be looking at real-time operation. So before we're looking at decades in planning, now we're going to be looking at fractions of seconds of operation. So this work is the non-cooperative games to control learn inverter dynamics of DERs. All right, so the motivation of this work comes from what could be a role that microgrids and DERs could have in a future electricity system. On one hand, they can bring resiliency to extreme weather events. So if you have a single microgrid, it can provide access to power when the main transmission network may have some outages. And then if you're going to start having a set of single microgrids deployed, it brings the question of what are the benefits of working with them as a network? Can you bring them together? Can they coordinate? Can they collaborate? And this is a figure from NROL portraying that. If we have two separate microgrids, what would happen if instead we can think of them as one unit if they're electrically coupled? What type of benefits would bring to the communities and to the grid? And then if we were to have these clusters or sets of microgrids, they can support the transmission network. So they could participate in the wholesale electricity market, and that's enabled by FERC 2222. So understanding that it's of value. And similarly, they could provide ancillary services if that's frequency regulation, spinning reserves, or others. So it's worthwhile looking at that question as well. So this work that I'll be presenting was presented at PSCC last summer. And it's the first student is Paul Serna-Torre, one of my current PhD students. Okay, so let's talk about more the problem setup and the motivation for this work. So if we have a set of DERs that could be, PV, rooftop PV, you could have batteries, different mixes of DERs you could have at your homes. You could think of them as what if you operate them together in tandem as a virtual power plant or as a VPP? And can you then be providing support to the upper level grid, if that's still the distribution network or all the way to the transmission network? And there has been quite a bit of work in this space on the control of VPP, as many of you might know. There's mainly two big lines of work. So one is looking at using optimization techniques to optimize that type of coordination. And there's a really, really large set of work here. Here, I'll just mention a couple works. This is not exhaustive by any means. But for example, Dalanes and his co-authors, they propose an online algorithm to control a distribution grid to solve the ACOPF while satisfying the output or a given output power reference. Similarly, Behi and his co-authors develop a bidding strategy for a VPP to maximize the profits from selling load following ancillary services, while also being mindful of the consumer preferences and the hourly operational constraints. So there are a lot of benefits to using optimization-based approaches. So on one hand, you can implement them online, and that's what we need from a practical perspective. So that's very important. They can be computed fast, which is also very important. So they have that going for them. However, they may disregard what if these agents are selfish and they have their own objective function? How are they going to be competing in that setting? So that's something that we see that from optimization techniques, they haven't captured yet. So that brings this other line of work, using non-cooperative game theory. Similarly, there's a really large body of work in this space. It's not exhaustive by any means, but let's talk about some examples. So in some past work, they have proposed a controller scheme that steers the state of the microgrid back to the nominal point by changing the input impedance of the storage. And similarly, this work by Chang and their co-authors develops a control scheme to coordinate DRs in an islanded microgrid to bring the frequency back to the nominal point. So that brings us to the research gap and the contributions of this work. So in terms of the gap, past work does not consider the nonlinear dynamics of DRs or of the inverters. In the non-cooperative game, they are working with dynamics, but they're not working all the way with the actual dynamics of inverters. They're working with, like state of charge of storage, that type of dynamical system, but not all the way to the actual dynamics of the devices themselves. And past work does not use learned state space models to represent these dynamics of the inverters. And similarly, the controllers don't get validated through using a high fidelity model of the inverter from the perspective of the dynamical system. So our work is the first that proposes the use of a non-cooperative game that does incorporate the inverter dynamics. And we learn a state space representation for the inverter dynamics that are going to be mimicking the behavior of a high fidelity model of these dynamics. And that comes from Sandia National Lab. That was in collaboration with them. They provided the high fidelity model. And our control scheme, we're able to show that what we'll propose, that I'll talk about in a few slides, is able to provide a regulation service that's requested from the upper level grid. And it is effective, and we show effectiveness in time domain. And we compare it with classical droop control and proportional control as well. All right. Okay, so let's look at the problem formulation. So as I was mentioning before, we have a set of DRs. You could have batteries, solar panels, you have a load, of course, over time. If you do nothing, you're going to get some uncontrolled power. So here's power on the y-axis, time on the x-axis, and it's going to be going to the upper level grid, whatever you may be outputting from your collection of DRs. But what if you have your DSO or TSO operator wanting you to follow an actual signal provided by them? So that's the motivation of this work. So to do that, we have certain assumptions and considerations of our control scheme. We are assuming that all DRs are going to be selfish, so each of them will have their own individual objective function. They're going to be grid following inverters, and we are going to be experiencing load perturbations. So then we see how the controller can be operate well in face of those perturbations. And we always want the power output from our microgrid or from our collection of DRs to actually follow the requested power by the operator. So if this is the requested power in red, we want our output from the microgrid to follow it as closely as possible. That's the objective. All right. So let's look at how we're modeling the inverters. So the first challenge is that we need a state space representation for the inverters or the DRs. And deriving the exact dynamics for the DRs may come with difficulties. So on one hand, there are privacy concerns. People might not want to share their internal dynamics of their devices. There are multiple control loops, and that creates high competition complexity, especially as you scale with a number of agents. And as I was mentioning, there are scalability issues for a high number of these inverters. So the approach that we took with this work that was like experimental, and we wanted to see if it would work, and it does work, was instead of posting all the analytical equations of the inverter dynamics, we wanted to learn them from the data. So that was the approach we took. The dynamics of each inverter were modeled through system identification, and we identified a transfer function for each of the inverters that we had from input-output time series data that we had from the high-fidelity model from Sandia National Labs. So that's the approach that we're taking here. So let's look into a little bit more detail of that. So basically, for each DR, we are going to have a set of time series that it's going to be our input our power reference input. So that's a time series, and we run a set of experiments, and that's going to give a set of outputs. So our power output from the DR, and with these pairs of input and output time series, then we can fit and do system ID to learn the transfer function for this given DR. And as we're changing the power reference, we're changing the operational point or the set point of our inverter. So then the dynamics are going to be changing. We're going to get different transfer functions. So then what we did, we took like an average or the one in the middle to try to capture something that works good enough for this range of set points that the inverter could have. So we get a transfer function for a DR, and from that we can write it in the state space representation. So we get matrices A, B, C, and D for each of the DRs that we have. So then for each DR, we have a linear system, basically, with this approach, if that makes sense. All right. And now we have a set of n DRs. So then we just stack the dynamics of them. So then we create this stacked set of dynamics where X is going to be the stack vector of the states for each DR. And then the control action is UI. And our power output is the vector Y, which is just the sum of the individual power outputs from each of the DRs. Okay, so then we have some considerations in our system. So we need to follow the power that's being requested from us by the DSO or the TSO. And we need to also serve our demand. So the power output from the collection of DRs minus the demand that we face has to follow this P reg that we're being asked. And to comply with the regulation service, we use a compensator to get zero steady state error. So that's what we're including. So that's going to bring extra states. So state omega, output V, matrices H, G, and D associated to the compensator. And last, we're going to be using the deviation of the states because ultimately we want to capture in our objective function. We want to penalize how deviated we are from the nominal conditions. So that's why we work with the deviation of the states instead of the absolute state. And with the compensator, the deviation of the states, we get the following augmented dynamics. The details of how we derive them are in the paper. Happy to share with you or talk about it. But ultimately, we get an augmented linear system with this setup that we have. All right, and now looking at the controller design piece. So we are setting this up as a non-cooperative game where each agent is competing with the other. So meaning that each agent is going to have an individual objective function, Ji, that's going to depend, it's a quadratic term on the deviation of the states. And also it's a quadratic term on our control action. And what's important here is that we are going to be constrained to the dynamics of our system, of all the inverters. So whichever controller we end up synthesizing has to be mindful of the dynamics of the inverters, of the entire VPP that we have, or the entire microgrid. So that's what's distinct about this work that prior work hasn't included. We are making sure that whichever controller we come up with does work with the physical constraint of the devices, if that makes sense, from a circuitry perspective and a control loop perspective. Okay, so the optimal controller is going to be linear on the states. So we need to find the matrices K and F. And we know from finding the Nash equilibrium, once we find it, there's no incentive for any agent to move away from that equilibrium, because if we do, that agent is going to be worse off. That's by the understanding of Nash. So then we're good to go if we find an equilibrium. From the literature, we know how that controller will look like. So we know the matrix R, that's by design. We know the matrix B, that's from our system. We don't know the matrix P, and we'll need information on the states as well. So then what we do to find the matrix P, we solve this set of coupled Riccati equations, and we do it in an iterative way because they're coupled. But we are able to solve for this matrix P to find this Nash equilibrium and this optimal controller UI for each individual DR. But that's not where the story ends. As I was mentioning before, yeah, we needed that matrix P that we found, but we still need the information about the states. So we need state variable information to then calculate that controller action UI. In our setup, there are no state variable measurements because they are all internal states because it came from system ID. So we're not actually measuring anything. So that brings a challenge. And to solve that, we use loop transfer recovery to basically create an observer and then get an estimate of the internal states of each of the DRs. And we use LTR in particular because we want to make sure that we are robust to any perturbations in the matrices A, B, and C for each of the DRs because these ones came from learning. So they are going to have errors. So we need to make sure that we're doing the best we can. So that's why we use LTR as opposed to a classical, more simple observer to account for any errors in the learning of the dynamics. All right, so let's put it all together so we see how this makes sense. So I'll walk you through this. So let's look at DR1. So this is one of our agents. It's going to have its internal dynamics. That's going to be giving some power output. And then it goes into the summation of the power outputs from all the other DRs. That's the total power output from our VPP or microgrid. And then we're going to be subtracting our load because we need to serve our own load. And then that difference is what gets delivered to the upper level grid, if it's distribution or transmission. Then we look at what we're sending and we compare it against the power that's being requested from us. And that error goes into the compensator. That's going to help us to achieve zero steady state error. And then from the compensator, we get the state of the compensator, and that gets fed into the controller or the control action that we are synthesizing that requires state information times the matrix K that we found, and also requires the compensator state. And with that, we can create the optimal control action from the game for DR1. And as I was mentioning, we need that information on the states, the estimates of the states. So that comes from this block over here, that it's basically that LTR observer where it uses output information, it uses control action information, and it comes up with an estimation of the internal states. And then each of the DRs has the same structure. So you get an estimated set of states for each DRs, and then you share them across the different agents. So that's the setup. And let's see how this performs basically in simulation and how well do the dynamics fit the actual high fidelity nonlinear system for the DRs. All right, so first we need to validate those learned dynamics to see if we are in a good space to use those learned dynamics to then synthesize a controller, because that's what we did. We basically learned the dynamics, and based on that, we used the non-cooperative game to come up with the optimal control action. So on the y-axis over here, we're looking at power output. X-axis, we're looking at time in seconds. And in blue, we're looking at the microgrid's power output from the learned dynamics. And then in red, we're looking at the same situation for the microgrid's output, but now using the high fidelity DR model from Sandia National Labs. So we see that both are pretty close. So the learning was really good in this case, and we are able to capture the dynamics of the DRs from the high fidelity model, which was exciting to see. And in this bottom panel, we're looking at power on the y-axis, same time x-axis, but here we're perturbing the load. So that is what creates these changes in our power output from the microgrid. This jumps in the load, basically. All right, so that being said, here we validated the learned dynamics to kind of say, okay, we are representing dynamics in a good way. So we can feel somewhat good or good about the controller that we're designing. But then when we test the controller, we are not testing it with the learned dynamics anymore. We are testing it with the actual dynamics from the Simulink model from Sandia National Labs, just to clarify that. So that's what we do here. Here, we're not using the learned dynamics anymore. We're only using the controller that we synthesized from the non-cooperative game, but testing it with the actual dynamics from the nonlinear model. So again, we see power on the y-axis, we see time on the x-axis, and we're comparing a set of different controllers. So our proposed controller is in red, and we see that it has faster settling times as compared to droop control or PI control. And we also have the power reference in black, in the dashed black lines here, as you can see. Also, our red controller doesn't show oscillations, which is something desirable. We wanted to converge without oscillations as much as possible. And it does achieve a zero steady state error because it gets to the power requested that we have to comply with. Everything's not perfect. We do have a little bit of higher overshoot, so more work could be done to improve the controller that we designed. All right, so then to conclude this work, we propose a novel control scheme using a non-cooperative game framework to coordinate all these DRs to provide a regulation service. But what's most exciting or interesting to me of this work is that for the first time, we incorporated the physical constraints of the DRs, which is something that hasn't been done in the space of non-cooperative games with inverters. and it works. So that's good. So we can feel good about being able to do this type of thing with inverters. And yeah, for the first time, we consider, in this case, learn inverter dynamics. And I think the use of learned states models can be promising, especially because we can have a lot of access to data like input output. So we could start thinking about implementing some of these techniques because the data could be out there. So now changing gears, looking a little bit about future work, and I would love to hear what some of you are working to see what you're excited about as well. So in this space of inverter dominated grids, I think there are a lot of open questions, which make it a really exciting time to working in that space. So because we have a diverse set of inverter manufacturers, they all have proprietary control architecture, so they don't share them openly. What are the specific parameters that they're using? What are the specific control architecture that you're using? They usually provide like binary files to give you the performance that it would do in, in transient or the dynamical behavior in general. And also the other aspect is that different operational points create different dynamics because it's a nonlinear system. So as your operational point changes, your dynamics are going to be changing as well if you're linearizing them. So this brings the time-varying dynamics aspects. So that brings a challenge. How are you going to be deriving and representing these aggregate time-varying dynamics of inverters? How are you going to work with the tractability issues that may come? So there's a lot of issues that we need to solve from a practical perspective of working with inverters. And to tackle some of these, I think that learning inverter dynamics could be a way forward, so a more data-driven approach. And of course, there's some work in this space, but a lot more needs to take place so we can feel confident about that approach. And the natural question is, how can we guarantee stabilizing solutions for ancillary services? As we're thinking about clusters of DR supporting the transmission network, then we need to be able to guarantee stability. And especially if we're going to be facing communication delays, which is what happens in practice, or if we don't have all the information available, or because of privacy concerns, not everyone wants to share the information, so you have only local information perhaps. How are we going to deal with that type of challenge? And to answer that, I think that stabilizing control techniques for large-scale time-varying systems is going to become really important in this space. And I think distributed and data-driven approaches could play an important role to try to tackle some of these challenges. All right. And then in this other future research, this is more looking at extreme weather events, how to make sure that communities have access to power when we are shutting down lines and generators for safety reasons. So this is an ongoing project that I have with a set of colleagues. So it's UC San Diego, where I'm coming from, some colleagues at UC Santa Barbara, UC Berkeley, NREL, LBNL, and Grid Lab. And we have been working on this for the last year and a half. This project's ending in the fall. And we're looking at basically how can we redesign the grid in California so it can be resilient to climate change or extreme weather events. And in this work, we have 4 different thrusts. One of them, we are understanding what's the likelihood of different communities with a census tract resolution. So meaning California gets split in roughly 9 southern regions. And then we're sending a survey and we have results and we're analyzing them at the moment where we look at what's the likelihood of electrifying transportation, of electrifying heat and different end uses. So we can have a modeling that's more realistic of what people are actually going to do or thinking of doing. And we're also capturing what type of subsidies would communities require to then electrify certain end uses because they're very cost prohibitive. So we need to understand what will be required from a policy perspective. And with that, it brings the question on, okay, now we know what to expect in terms of electrification, DR deployment. How can we now develop microgrid sizing and operation and this coordination of transmission and distribution? And similarly, looking at just DRs and coordinating with the transmission network. And last but not least, we also need to understand if we're assuming this future where DRs are going to be supporting the transmission network and also providing local power when the transmission network it's not operating or has certain portions powered off, what are the new tariff schemes that we need to have in place so people actually have an incentive to participate in these new services that we are thinking they're going to be providing? And with that, I'm very grateful to the technical advisory board that we have, PG&E, Southern California Edison, and the Sacramento SMUD has been supporting this work and bringing feedback into how we're looking at this question. Similarly, very grateful for the support from NREL and Grid Lab as well, and LBNL. And with that, I'll be happy to take any questions you might have or talk about the work that you're doing. And yeah, thank you for joining today. Yeah, go ahead.
Okay, so we're just going to ask us 10 questions. Other questions? You want to ask yours first?
Yeah, great presentation, by the way.
Thank
And motivating. So when you mentioned about the system identification that you did learn the state space models for DRs, how did you design the input signals that were fed to the
Yeah.
models?
Yeah, exactly. Let me go back to that slide. Yeah. So for this one, so basically we did a range between going all the way to as low power as possible, all the way to the rated power. And then we divided that in like 10 intervals, if I remember correctly. So then we could see as we changed the operational point, how the transfer function that we were getting was changing. So yeah, of course it was changing. And then we chose one like a median transfer function in hopes that it would perform well. And yeah, in practice, it does work pretty well. But I think this work requires a lot more understanding and grounding on when does this type of method breaks, what considerations we need to take in this like data-driven approach. For me, this was an experiment of seeing, does this even work? Like, is it even worthwhile trying to do this? And the fact that it does, then that led to the next line of work that we're looking at, thinking, okay, what are the guarantees and what can we say when this might break? And also I'm thinking about, as the transfer function changes, I want to post it as a hybrid system instead of just choosing a median transfer function, actually post it as a switch affine system. So depending on where you are in your operational point, you go to the actual more accurate representation of the dynamics. Yeah. Yeah. Thanks for asking. Yeah. Yeah. Go ahead.
What do you think would be the most helpful like data set software for this to add to this space with like for your work and stuff?
Yeah, so if we would have a way to always record like input and output from our DRs, that would be what we're requiring in this space. And from a practical perspective, that is possible because you have your DR, you could have the measurements of what's the power that you're outputting, and yeah, we do have that. And the key part would be, let's have like a microcontroller locally that can then learn the dynamics of your inverter. And yeah, that technology exists, it's out there. It's more a matter of, are we interested in doing that? Is the DSO interested in getting the support from, cluster of DRs? But yeah, I think in terms of data, we would have it, which is exciting. Yeah. Yeah, thanks for asking. Yeah, go ahead.
I have a question that's on the first part of the
Mhm.
presentation. You mentioned that in your transmission expansion model, you were co-optimizing both the investment and the operational decision.
That's right.
How you did that on the operational side, especially how you model things like the fact that on a day-to-day basis, decisions are made on forecasts, they're made with a limited horizon. So I'm wondering how this shows up in your model.
Yes. So in the other work I showed, so basically we have perfect forecast for the load, perfect forecast for the hourly capacity factors. So basically you knew what you were facing. Yeah, so basically we had perfect foresight on that end. So then you could really optimize and say, okay, this is the optimal capacity for the line to build, the optimal way to operate, the optimal power transfer. However, this could be set up in a stochastic manner. It has a capability where you say, these are the possible future scenarios, and then build some plan that would be robust against these future, hourly capacity factors or these potential scenarios for loads. But in the paper that I show, it was all deterministic. Yeah. Thanks for asking. Yeah.
I have more questions on the next question. I'm sure Sergio probably has more questions. But I don't want to take it. Just so I have great ones.
Maybe I'll ask one.
Yeah.
So on the planning,
Mhm.
the first part, the planning problem, oftentimes the batteries are used for many different purposes. services, right? Do value stacking
Mhm.
on these batteries. Here with these long duration battery storage models, is that still an assumption? So it seems like the assumption is it's only used, that, you know, the batteries you're installing are only used for these sort of steady state, longer term non-regulation.
Exactly.
Is that the assumption you made? And if so, is that the typical assumption that people make in this space, or?
Mhm. Yeah, that's right. That's the assumption that storage would only help with energy arbitrage or, hourly resolution all the way to during seasonal arbitrage. And yes, that's usually the assumption. We don't look at frequency regulation or ancillary services. We can model spinning reserves. And then depending on the rules that you have, you can encode whichever rules would be appropriate or also include like capacity markets, so capacity constraints. But yeah, we basically simplify drastically the dynamical side. We, at most, with the spinning reserves, but that's usually the approach. Yeah,
Got it. Do you have a sense of how much that
that would change.
it changed? Like if you,
Yeah.
at least that's my understanding right now, is a lot of batteries are being installed for these shorter term considerations.
Yeah. No, I haven't looked at that question, but I think it's super important. Yeah, at least, yeah, in California, they have been deploying, well, and in the US, like 2 to 4 hours, it's like mostly. And in California, they are arbitraging between like noon and then the evening. So they are focusing on that. But of course, yeah, they are looking at frequency regulation as they are the resources that can kick in almost immediately. Yeah, well, the prior work, because it was more focused on long duration storage, that type of technology may not support. Well, it depends on the specs ultimately. If they can respond fast, yeah, it could change for sure the results that we get. But if they're on the more inefficient, slower side, then yeah, I would say more the seasonal aspect. But yeah, I think absolutely it could change quite a bit depending on how much can you get out of that market for sure. Yeah, thanks for asking. Mhm.
So you mentioned that the state space is estimated, not the right measure.
Mhm.
Do you experience any like error accumulation with estimates, or is that compensated by measuring your power regulation error?
Yes, so it worked very well from this part because as you were saying, we were doing state estimation and we were using like the actual power output that we were observing and the actual control action that was being decided. So we didn't see that things were converging into the wrong direction. Like the error was always pretty minimal. So yeah, it worked fairly well, which was very encouraging. Yes, yeah. Thanks for asking.
Yeah, we're coming up close to the scheduled time. You guys have questions, maybe. So, Eddie, you said you can stick around for
Yeah.
afterwards.
Yeah.
Any other questions for people besides Matthew and Sue? Well, thank you, Patty.
Yeah, thank you. Yeah, thank you for having me.